Welcome back to Statistics. It's Monday, March 23rd, our first day back from spring break, our extended or disrupted spring break, however you want to look at it. And I hope you've been doing well. I hope you've gotten my previous messages and had the time to look at the videos that I posted. Today I'm going to follow on with those with a summary of confidence intervals, and then we will continue moving on through new material this week, as well as have a few more online assignments. So yeah, let's get right into it. So the video I posted earlier, and by the way, if you haven't seen that, check your announcements or your on the announcements on WebAssign or your email for an email from me. We went through an example for confidence intervals for a mean. And this is our first real foray into statistical inference. The purpose of a confidence interval is to estimate the mean and of a distribution. And here we're going to assume a normal distribution. So we're trying to estimate the mean of a normal distribution. And as I said, the previous video took us through that in a case, a certain case. I think we were trying to estimate the mean height in a certain group of individuals. But the ingredients in any confidence interval, it's a pretty short ingredient list. First of all, you're going to have a confidence level that specifies the level of confidence that you have that the interval that we're calculating actually contains the true mean. And then there's the sample mean x bar is going to play a big role in building our confidence interval, as is this concept of the margin of error. The end result of all this will be a confidence interval. It's usually written in the terms that I've got here: x bar plus or minus m, where x bar is your sample mean and m is the margin of error. Sometimes it's also written in this interval notation, where you just give the lower bound x bar minus m for the interval and the upper bound x bar plus m. So computing the margin of error involves this formula here. It's what we call a critical value, and that's this z star, times the standard deviation of x bar. And this guy comes from the central limit theorem. So this sigma divided by root n that you see here, that is the standard deviation of x bar. And as we explained in the previous video, really all this is saying is z star is telling you how many standard deviations of x bar you need in order to get the desired confidence level. In particular, the way you compute z star is you're just looking for the middle whatever percent of a standard normal distribution. So the whatever percent corresponds to your confidence level. So if we were trying to compute a 90% confidence interval, my critical value z star would be the upper bound of that middle 90% of the standard normal distribution. So yeah, that's it in a nutshell. That's what's involved in computing confidence intervals. Let's go through a quick example here, and we'll see how that plays out. So here, what I'd like to do is consider an example where we're looking at the average amount of cereal in a box. Of course, cereal boxes come in different sizes, but let's consider one in which the net weight advertised on the box itself of cereal is 12.8 ounces. And so what we want to know is, well, is that really accurate? Does every box of cereal weigh 12.8 ounces? Well, probably not exactly, right? So, well, how do you know you're not being ripped off? Well, one thing you could do is go out and buy a bunch of boxes of cereal and just measure them. How much cereal was in each box? So let's do that. Suppose this is the data we got back. Suppose we went to the trouble of taking a random sample of whatever cereal we're talking about here. Maybe it's Cheerios. And we get, in this case, 10 boxes of cereal, and we measure very accurately the amount of cereal in each box. We wouldn't expect each box to weigh exactly the same thing, and that's indeed what you see in the data here. So the first box of cereal we got weighed 12.85 ounces, a little bit more than the average weight. The second one weighed 12.794 ounces, a little bit less than the average weight. So if you were the person who got that second box of cereal, I guess you'd be in store for some kind of refund, maybe. And then you see that same kind of variation in all 10 boxes of cereal. So let's consider this a simple random sample from the population of all boxes of cereal, of whatever brand we're talking about here, Cheerios, I guess. And let's use these 10 measurements to find a 99% confidence interval for mu, the true mean amount of cereal in a box. So we're going to use the amounts in these 10 boxes to try to give an estimate for the true average amount of cereal across all boxes of cereal of this particular type. Okay, notice we're asked to assume that sigma, the standard deviation of the weight of cereal in a box, is 0.03 ounces. This is a fairly standard assumption. We talked about it last time. We don't have to actually make an assumption like this. We'll see how to get around it a little bit later. But for purposes of illustrating the basic process, we're going to go ahead and make that simplifying assumption. So yeah, we need to compute a confidence interval here. How would we do it? Well, we're going to make another assumption as well. We're going to assume that the weight of cereal in a randomly chosen box is normally distributed. So X equals the amount in a box. It has a normal distribution. Of course, its mean is unknown. That's precisely what we're trying to estimate. But its standard deviation is 0.03. So to compute the confidence interval, we simply need x bar plus or minus mu, m, where m is the margin of error. So to compute x bar, what we need to do is just take the average of those 10 guys there. And I don't know if you can see this, maybe not, but I just put those measurements in my calculator, those 10 data points in my calculator, and I'm going to use one variable stats to calculate that. So stat calc one variable stats. Mine was in list 1, so I do that, and I find that x bar is 12.8399. So that's the first step. X bar is 12.8399. That is called the point estimate for mu. In other words, if I had to make a guess right now as to the value of the true mean, mu, I don't have any better information than just the mean of the 10 boxes that I have. And so x bar is called the point estimate for the true mean, mu. So next we need to compute the margin of error, and if you'll recall from the previous slide, that's your z star times sigma over radical n. So there's really two pieces of that. There's the z star value. That's called the critical value. Let me just do that right here. The critical value z star. So what we want there, since it's a 99% confidence interval, I need the upper bound of the middle 99% of the standard normal distribution. So I'm just going to make a quick sketch here. This is the standard normal distribution. Normal would mean 0, standard deviation 1. There's 0. And I want the middle 99%. So that's going to be a pretty good hunk of the whole curve, right? In fact, 99% of it. So this middle area is supposed to be 99% or 0.99. And I need to find what that upper bound of it is. Well, the upper bound, you can calculate from just the left tail, right? There's 99% in the middle, there's 1% left over, so 0.5% in both tails. So Z star is actually the 99.5 percentile of the standard normal. So Z star would be inverse norm of 0.995, comma 0, comma 1. And I'm just going to grind that out with my calculator as well. Sorry about all the shadows here. Second distribution, inverse norm, 0.995, comma 0, comma 1. And bang, I get 2.5758. Round these numbers to 4 decimal places is always a good practice. So that's my Z star value, 2.5758. And let me go over here to finish the computation. So then the next thing I need, once I have Z star, is the standard deviation of X bar. That's the sigma over radical n. So that's going to be our 0.03 divided by the square root of our sample size, and that's 10 because we have 10 different measurements. And so just banging that out real quick, 0.03 divided by 10 raised to the 0.5 power, which is a quick way to calculate square roots, by the way. So that's 0.009487. 0.009487. I'm rounding that to 4 significant places, which means, of course, that I'm ignoring those leading zeros, then round to 4 places after all the leading zeros. So our margin of error then is going to be Z star times standard deviation of X bar. So that's just this number times our Z star value. So I'm just going to do that real quick, times 2.5758, and that gives me 0.02444. Again, I've kept 4 significant places there. So that's my margin of error, about 0.024 ounces. And so the confidence interval is X bar plus or minus M. So that's going to be my X bar value, which was 12.8399, plus or minus that margin of error, 0.02444. And so, yeah, let's just work that out real quick. So 12.83999 minus that 0.024 gives me a lower bound of 12.82. I'm rounding these final values to, I actually ought to round to 3 places because that's what my data was given. So that's 815, and then the upper bound would be 12.8399 plus the 0.0244. And just working that out, I get 12.864. So what this means is that we are, and sorry about the mess up here, we are 99% confident that the true average amount of cereal in a box is between 12.815 ounces and 12.864 ounces. So that is another quick example of doing a confidence interval when sigma's known. Again, we'll look at the case when sigma's unknown shortly. I wanted to end real quickly by talking about a couple of properties of the confidence interval, and what it tells us. So let's think about for a minute how confidence intervals behave. The key to that is, again, thinking about the margin of error. It's a function of z star, your standard deviation, and your sample size. And as far as z star goes, there's really not a formula to keep in mind. You really want to keep this picture in mind. Z star is the upper bound of that middle area in the standard normal distribution, where the area we're talking about is the confidence level you want. So one thing to you can see from this picture is that if you want more confidence, if you want to increase the confidence level, then that's going to increase the margin of error. Why is that? Well, increasing the confidence level C means making that middle area there bigger. And so when that happens, that's going to push the upper and lower bounds out. In particular, Z star will get bigger. And since Z star gets bigger, your margin of error gets bigger. So increasing the confidence level increases the margin of error. On the other hand, increasing the sample size decreases the margin of error, and that's because the margin of error is the sample size divides into the margin of error, right? The margin of error is the z star times sigma divided by square root of n. So if you increase n, you're dividing by a larger number, and that tends to make the margin of error smaller. Actually, because of the square root, if you want to have the margin of error, you have to actually quadruple the sample size. So that's those are some important facts to keep in mind about the way confidence intervals behave as you change the sample size and the confidence level. Finally, let's take a look at this term margin of error. What kind of error are we having margin against? In other words, what does the margin of error take into account? Well, again, one idea here to keep in mind is what the margin of error is. But the upshot of all this is that this is just all coming from the central limit theorem, facts about the normal distribution. And so the only thing the margin of error is really taking into account is the random sampling variation in x bar. This refers to the idea that x bar varies from sample to sample, and so when you're looking at a particular x bar value, it probably does come from the middle part of the normal distribution, but there's a chance it doesn't, and that's what the margin of error is taking into account. I wanted to show you this nice picture from the book, if I can find it. Let me see, it's under here. Here we go. This picture kind of illustrates what we're talking about when we talk about random variation in x bar. The bell curve you see there is just the normal distribution we're trying to find the mean of, and you see the mean is right there in the center of it. And then below you have these little goofy lines here. Each has a red dot in the middle. The red dot is actually an x bar value from the sampling distribution of x bar, right? So and then to the left and right of each x bar value, you see an arrow extending, and the length of that arrow is the margin of error. So the whole thing from the left endpoint through the x bar value to the right endpoint, that's your confidence interval. Notice that in each of the, and what you're doing here is just looking at a bunch of different X bars that were possible from this sampling distribution. So in each of these cases, the margin of error is the same, right? Because the margin of error doesn't depend on X bar at all. Um, and the margin of error is scaled for like a 95% confidence interval, so that 95% of the time, the true mean, which is represented by this vertical line here, is within the confidence interval. Um, and so that margin of error is taking into account the fact that the X bar is jumping around. Sometimes it's bigger than the mean, sometimes it's less than the mean, sometimes it's a lot bigger than the mean. But the X bar is sized to just the degree that, if this were a 95% confidence interval, 95% of these lines would in fact contain the true mean. Now occasionally, even in the best of circumstances, you'll get an X bar out here in the tail of the sampling distribution, and the margin of error, although correctly sized, is just not going to do the job because that X bar is so far out in the tail that the confidence interval is not going to be containing the true mean. That's just a fact of life. That's why it's called a 95% confidence interval instead of a 100% confidence interval. But that's what is the margin of error is doing. The margin of error is making it the case that most 95% of these confidence intervals really will contain the true mean. But the important thing to remember is that sampling variation is the only thing that confidence intervals take into account. So, for instance, if you've got other issues with your sample, like things we've talked about, undercoverage, voluntary response bias, non-response, wording effects, response bias, so on and so forth, none of those are going to be taken into account by the margin of error. So all this fairly fancy statistical inference that we're doing can't make up for bad, sampling design or bad experimental design or just bad data. So that is it for today. This should help you finish homework 27, and we're going to move on next to the next topic in inference, which is significance tests. So be looking for that video very shortly, probably Tuesday. In the meantime, if you have questions, please email me. I hope everything's going well on this first day of our online Hampden-Sydney experience. In the meantime, take care, stay well, and stay in touch.